our example 2, we can say that if A bar is equals to rho cos phi of A rho plus sin phi of A phi bar, comma, then we can say evaluate the line integral around a closed path, below. Around a closed path below. Hence, verify Stokes theorem. Hence, verify Stokes theorem. That is our question that we are supposed to look at, and the closed path is this before any other thing. So now that is my closed path that we have. So we want to verify Stokes theorem for that, and we need to know how Stokes theorem also states. So in our Stokes theorem, so we need to know how to state our Stokes theorem, and so we can say this: according to Stokes, we have our line closed loop or our line integral being equals to the curl of the surface here. That is our Stokes theorem. So we need to start with the left-hand side again and show that the left-hand side must be the same as the right-hand side. So we can say, taking the left-hand side, so if we take the left-hand side, then this is what we have, A dot dl. So we want to represent that. Now, maybe we should come back and look at how our closed surface looks like. I mean, this is point A, this is point B, this is point C, and that is point C. So look at the movement from A to B, B to C, C to D, and back to A. Now that is our closed path. And you can see this is a line from A to B is a movement in a line. B to C is also another movement in a line. C to D is another movement in a line back to A. So this is our closed path that we need to represent. So we are going to represent that closed path as the integral from A to B plus the integral from B to C plus the integral from C to D, then plus finally the integral from D to what? To A of that closed path of what? Vector A dot D L bar. So we have to take each portion at a time. Now, maybe before looking at that integral from A to B, we can come back and look at this drawing keenly. You see, normally, if I was to draw that, first of all, we need to know the coordinate system. We can see we have rho and phi. Yeah? So definitely, without even being told anything, this must be cylindrical coordinate system because of rho and phi element. Yeah? So if I was to draw my cylindrical coordinate, I want to give you a clear picture of this. We have that. I'm just having a small sketch, and we have that, and we have that one there. So this is Z, that is Y, and that is X. This is part of the cylinder. That. We have that, it's just a sketch to that point, and that point. So, sorry. That is what I have as my cylinder. If you are so keen with whatever we have, it is in the XY plane. So this is X and this is Y plane. So this thing is either at the bottom or at the top. But for us to pick positive values, I prefer using maybe the top or the bottom. Any can do. Now, let us assume that this is where we have our 5. This particular arc here, or the radius there, it's this, 5, and then 2 be this. That is 2. Then from the y-axis, which is this, we have somewhere like so. Again, from the x-axis, which is this is also what we have. Now, we are interested in this closed path here. That is a clear picture of what we are working with. This path is the same as what has been drawn there in the question. Now, this is my closed path. Here on the y-axis, this is point A, this is point B, that is point C, and that is point D. So that is the picture of whatever we are working with. So the angle may be, along the x-axis, which is this is 30 from there, and this is 60. So we go back to our question and see if we can be able to get the line integrals of those particular values. So we are back here. So maybe because we want to integrate, so we want to integrate individually path A to B, B to C, C to D, D back to A. So maybe I can say along, because I'm doing individual integration, along AB, so along AB, we need to look for the constant term. Now come back here to your drawing. Along this path AB, from A to B, the constant term is the radius. And the radius of the cylinder at this point is 2. You see, at point A, the radius is still 2. At point B, the radius is also 2. So along that particular path AB, the value of rho, which is our radius of the cylinder, is equals to 2. And whatever is changing now, what is changing here? So that one also is very important, because I'm moving from A to B. Whatever is changing is the water. Our length from A to B also will be important. So what is changing from A to B? The angle is what is changing, because we have an angle at point A, the angle is 60. At a point B, the angle is 30. So the angle is changing. So definitely we'll get our direction of DL. So then we can say along that path, DL bar. Remember, the angle in cylindrical coordinates is phi, and so the differential length along A phi must be rho d phi of what? A phi bar. So these are the two components that we need, so important, because you see, we'll be working with DL, which is this, and we'll work also with the vector A, which is also given up here as this value. So let us continue. So we are saying that after getting that, we can go and do our integral and say that from A to B, A bar dot DL bar will be the same as from A to B, the angle phi is equals to what? At point A here, the angle phi is 60. So you can see from x-axis up to this point, it is 60, and the angle B is what? 30. From the x-axis to that point, it is 30. So we'll say that phi will be 60 degrees all the way to what? 30 degrees. Then we have A as being rho, the cosine of phi, A rho, plus the sine of phi of A phi bar. Then we are dotting with DL. So we'll say dot rho d phi of A phi bar, like so. That of A phi bar. Now, remember our dot product rule that if we dot A phi and A rho will give us a 0 because they are opposite. A rho dot A phi is 0, but A phi dot A phi must be 1. So that is what we are applying. So this term will disappear after doing the dot product, and we'll be left with this term and that term alone. So we are saying that from there we'll have our phi being 60 degrees and 30 degrees. This has disappeared and I'm left with rho sine phi d phi, like so. Then I can do my integration. We can do my integration, but also you need to take note that we are only integrating with respect to phi, so the value of rho is given as a constant 2 along AB path. Yeah? So let us continue with our equation. So we have this to do an integration on. So if I continue, because rho was a constant, so I'll indicate a 2. And if you integrate sine, you'll get negative cos of phi, like so, with my limits from 60 degrees to what? To 30 degrees. So this translates into 2 into the cosine of 60 degrees minus the cosine of 30 degrees. And with a good calculator and value, if we punch that, we are going to get we'll have the root of 3 over 2 minus we are going to have a half minus the root of 3 over 2. And so this translates into 1 minus root 3 as our answer. So that will be our answer for that. Then now we are supposed again to integrate along the path. If we come back here, now we are from A to B. Now we are supposed to go to B to what? To path C. So along path BC, so along the path BC, so we are saying that along path BC, so again we need to find the constant terms. So along path BC, what is constant? So if you are very keen again, the angle here is 30, which is the same as this angle. BC, the angle is not changing. So it's only the angle that is what? Constant. And what is changing is the length or the radius. So rho changes from 2 to what? To rho is equals to 5. Yeah? So we are saying that along path BC, phi is equals to 30 degrees and rho is equals to what? Rho changes from 2 to 5. So our DL will be the value in the direction of rho, and that value must be d rho of what? A rho bar. d rho of A rho bar. Then we can work out again. I can say maybe therefore from B to C of AL dot DL must be, we have the value of rho changing from 2 to 5. Value of rho is changing from 2 to 5 of the term rho. We have rho cos phi in the direction of A rho bar plus sine phi in the direction of A phi bar dot d rho of what? A rho bar dot d rho of A rho bar. So again we apply our dot product rule. If we dot A rho to A rho is 1, but A rho to A phi will be 0. So this term will disappear finally. That goes as 0, and we are only left with this and that. And so this translates into rho is equals to 2 to 5. Then I have my rho, the cosine of phi of what? D rho. Cosine of phi of d rho. Then let us continue. So we know that our angle was what was constant. It was 30 degrees. So the cosine of phi becomes constant because we are only integrating with respect to rho. So we'll have the cosine of 30 degrees as being constant. If you integrate rho, we'll have rho squared all over 2. Limit from 2 to what? To 5. 2 to 5. And if we compute that, we'll have cos 30 degrees over 2. I've factored out the 2. Then this gives you what? 25, the upper limit, minus 4. If you simplify that further, we are going to get 21. This is 21 root 3 over what? 4 is our answer if you compute that. Then now we are supposed to look at it again along the. Now next it's along path CD. Now along path CD, 5 is constant, which is our radius. Then what is changing is the angle from C to D. We can see our angle here is 30. Then the angle at this point is equals to what? 60. So then we can have that, which we have rho is equals to 5, and dl will be d rho dot, and the direction is a phi, like so. So let us do our integration. Let us do our integration. So we are integrating from C to D of A bar dot dl bar. This will give us the value of phi. At C, the angle is 30. So we have this as being 30 degrees, and this at D, the angle is 60 degrees. Then the value of A, still it's the same as the other one, rho cos phi of A rho plus sine phi of A phi dot dl, and my dl still it's rho d phi of A phi, like so. So once again, if I dot, this term disappears and gives me a 0, and I'm only left with that because of A phi dot A phi. So this translates into phi being 30 degrees to 60 degrees. Then we have rho, the sine of phi d phi, like so. So rho is a constant, and we have its value here as being what? 5. So I can substitute that 5 And if I integrate sine, gives me what? Negative cos phi. I'll insert my limits from 30 degrees to 60 degrees. This translates into 5. The cosine of 30 minus the cosine of 60 degrees, like so. And if you do a translation of that, if you finish up that value, we are going to have our answer as being what? 5/2 into the root of 3 minus 1. 5/2 minus 5/2 into the root of 3 minus 1. Then finally now, we can look at it now along the path what? dA. So the path dA again, if I come back to this, path dA is the same as path BC. But what happens? It's only that the lower limit will be 5, the upper limit will be 2. What is changing is the radius, and the angle also, at this point it is 60, not 30 like what we had in BC. So, so we can say along path dA, so along path dA, so the constant term is phi, and phi is equals to 60, and the changing term is rho. So our dl definitely must be in the direction of a rho, and that will be d rho in the direction of what? A rho. It will be d rho in the direction of a rho. And so we can say therefore the integral from d to a of a bar dot dl bar will be, now from d to a, phi, rho at point D, rho is equals to 5, and up here it is 2. Of a, the value of a is given as rho, the cosine of phi of a rho plus the sine of phi of a phi bar, then dl, and my dl is dot d rho of a rho. So just like the other one, what disappears is this term, because of a rho, a phi gives you a 0, so that will disappear, and I'll be left with this and that alone. Yeah? So this translates into rho is equals to 5 to 2. This to this will be the same as rho, the cosine of phi d what? D rho. Like so. And we've realized the angle is what is constant, then definitely cos phi is constant. And I'll have the cosine of 60 degrees, because our angle here is 60 degrees. If I integrate rho, I'll have rho squared all over 2 exactly. Then we have from 5 to 2. So we can take our 2 outside, and we have the cosine of 60 degrees over 2. And then we have 2 squared is 4 minus 20 what? 25, which is 5 squared. And finally, that will also translate into, if you simplify even the cosine of 60, we'll have negative 21 over 4 as our answer. Negative 21 over 4 as the answer. Then we'll sum up all our results. Remember, we were adding path AB, path BC, path CD, and path DA. So if we sum up all our results, so we can sum up and finally enclose our path. Yeah, it's a very tedious example, but it's okay for for exam purposes. So we are saying that summing up the results, we are going to have so my first value was 1 minus the root of 3. So I'm adding that to the next one was 21 root 3 over 4, then plus 5 over 2 of the root of 3. So if I simplify that, root of 3, I've opened up the 2, again minus minus 5 over 2. Then finally my final result is here, minus 21 over 4. So if you simplify all this, I expect you to get this answer as 27 over 4 into root 3 minus 1 as your final answer. Or you can simplify that and get a decimal value. That was only the right-hand side of Stokes' theorem. So now we want to look at the left-hand side. This was the left-hand side of Stokes' theorem. Now we want to take the right-hand side. So say taking the right-hand side, So our right-hand side was S into del cross A bar dot ds bar. Now here it's very important first, before trying to implement this value, let us find what is here. Yeah? What is the curl of A? Yeah? So now we can see here that curl A, or del of A bar. Now again, our coordinate system is cylindrical. And remember the formula that we had for cylindrical coordinate system. It's also very important. So we are saying that the curl of A in that situation is 1 over rho into A rho. Then we had, remember what we said here, that it is rho A phi. And then finally we have A z. Then we have partial what? Rho. Then we have partial phi. Then we have partial z. So then we have these values here. So this is the first one in the direction of rho. The values are here. So we have this for A rho, this for A phi. Yeah? So we are saying that this will be rho, the cosine of phi. And remember, because there's another rho here, you must put that rho there first before going to this particular value, this. So we have that rho, then we have to include now sine phi. Then we are not given anything in the direction of z. So the direction of z must be what? 0. Z must be 0. I don't need this. So now we want to do a determinant method. Actually, this is a good example because it has included divergence, and now we're also having a curl. So it's actually constituting of what we've just covered in our lecture today. So we can factor out that term outside the bracket. So we can have our direction in the arrow direction. Then we have that. And in the arrow direction, that. Then we have that. We have rho sine phi, partial z, then 0. Then normally the next term negates. So we negate that, and we have rho A phi, and the determinant Then we have partial rho. Then we have rho, the cosine of phi, partial z and z. Then finally we have plus in the direction of az bar. Then we have partial what? Partial rho, I hope the space will be enough, cos phi. Then we have partial phi. Then this is rho sine phi. Rho sine phi. Then that, and we can close our bracket. Now from there, then we can do our determinant. It's mathematical a bit. So if you look at this keenly, this is 0. Then here, because we are differentiating with respect to z and there is no z term here, so this will be a rho in bracket 0, nothing here. The solution becomes 0. Then minus rho in the direction of a phi. Then again here, this to that is 0, that to that also is 0 because we don't have a z term here. So that translates into 0. Then in the direction of z, now we have that plus az, and we are differentiating this with respect to what? To rho. So this will be, if we differentiate that, we are going to get, this will be 1, and we are left with sine phi, and then normally we subtract the other one. So if we do a subtraction of the other one, and if we are differentiating cos is minus, and so this translates into plus, and you're going to have what? Plus rho cos what? Cos phi, like so, in the direction of az. So that is what we are going to have as our solution at that point. So if we open up our bracket, this is this versus that, this is sine, minus sine, and so it translates into sine. Sorry for that. So that if we have this, we can now rewrite it as 1 over rho into sine, and sine is a common term, so we can factor that out, and we are left with 1 there plus rho. And we have what? Sine phi, direction is what? Az. Direction is az. Now we've worked out this particular term that is in bracket here. So already we found that, and we've seen that the direction is in the az direction. Then now it's very important that now we get ds from what we had done, the differential surface, ds in the az direction. Yeah. So what is going to be our ds in the az direction? So I can also say this here, that also ds bar, now we're trying to get that in the az direction, must be rho d phi, d phi in the what? Az direction, yeah? Rho d phi in the az direction. This one is found from our differential surfaces that we did previously, yeah? It is the same as that. So now we want to dot this to this. So when we dot the two, so I can write here and say maybe hence that integral of this cross a bar dot ds bar will be the same as the double integral of this term of mine, which is 1 over rho into 1 plus rho sine phi ds is that, because az dot az will disappear, so there's no need of writing that. So this is rho d what? D phi. So because I have rho and phi, yeah, I need to go back to my question and check the limits of rho and also check the limits of phi. If you look at our drawing that we had initially when we started our question, you can get the limits of rho from the drawing, and rho was our radius. So our radius was ranging from what? It was from rho is equals to 2 to 5. And the angle was also ranging from phi is equals to 30 degrees all the way to what? 60. So those are our limits there. Now, we can simplify that. Again, you can see this row and this row will cancel, and I'm left with only this term alone. So let us simplify that, and we finish our question. So, if you simplify that, we have rho is equals to 2 to 5. Phi is equals to 30 degrees all the way to 60. Then I have 1 plus rho, the sine of what? Phi, d rho, d what? D phi. D rho, d phi. So if you integrate sine and if you integrate this term, and we are through with our question. So that if I integrate 1, I'll get what? Rho. If I integrate rho, it gives me rho squared over 2. Limits of integration are 2 to 5. Then if I integrate sine, you'll get negative cos. Limits are from phi is equals to what? This is rho. Phi is equals to 30 degrees to 60. 30 degrees to 60. Then if you play out with that, if you put your limits there and there, then we're going to have the root of 3 minus 1 for this term here, all over 2 into, if again I put my limits for the other one, 5 to 2, this gives me 5 for that, plus 525 over 2, minus 2 plus 2, which is 4. Actually, it is 4 over 2. So this will translate into the root of 3 minus 1 all over 2 into 10 plus 25, that is 35 over 2 minus 4, and that finally translates into 27 all over 4 into the root of 3 minus 1, which is equally the same as the answer that we got in the previous working. So again, we've been able to prove our divergence theorem. So maybe next time when we meet, we look at more questions related to vector analysis, because these two theorems actually winds up vector analysis. And after looking at those questions, we'll straight away go to electrodynamics, which was supposed to be which is actually our second unit, and we'll look at electrostatics. Thank you.